Hello everybody and welcome back. We're going to be tackling the last question on the Grade 9 2012 Fryer paper put out by the University of Waterloo. So let's take a look at our final question, question number 4, right now. Alright, so in the preamble they're giving us two formulas. The volume of a cylinder with radius r and height h equals pi r squared h. The volume of a sphere with radius r equals 4/3 pi r cubed. Okay. So A part. The diagram shows a sphere that fits exactly in a cylinder. That is, the top and bottom faces of the cylinder touch the sphere, and the cylinder and the sphere have the same radius. State an equation relating the height of the cylinder, h, to the radius of the sphere, r. Okay. So let's redraw our picture a little bit. It's a light bulb question, so we can expect it to be somewhat short in terms of computation. Alright, we have a sphere in here. We want to relate the height and the radius. Well, since the sphere exactly touches the top and base of the cylinder, then we can see the height is going to be exactly 2 radiuses. Right? They're going to form a diameter of the sphere. So what does that mean? Well, h is the diameter. Well, what's diameter? That's 2 times the radius. So h is equal to 2r. Simple enough. Alrighty. So that was A part, fairly simple. Just needed that final answer, h equals 2r. Now on to B. For the cylinder and sphere given in part A, determine the volume of the cylinder if the volume of the sphere is 288 pi. Okay. Well, what did we just learn? We learned that h is 2r. So the volume of the cylinder, which we'll write V cylinder, that's going to be what was it, pi r squared h. That's going to be pi r squared 2r. We're substituting in our value of h. And that's going to be 2 pi r cubed. So if we could just figure out what r is, we'd be all set. Well, we know that 288 pi is the volume of the sphere. And we know that the volume of the sphere, in terms of the radius, is 4/3 pi r cubed. So then r cubed is going to be 288 pi divided by 4/3 pi. Well, these pi's are going to cancel each other out. And you're going to be left with 288 divided by 4/3. That's going to give us 216. Well, fortunately, 216 is a cube of a nice little number. It's going to be 6. So the cube root of 216 is 6. That's something I have memorized, and maybe if you do enough of these contests, or you just like writing out powers, eventually, yeah, you'll probably realize that 216, immediately it pops in your head, that's 6 cubed. Alright, so now we know the radius is 6. So the volume of the cylinder is 2 pi 6 cubed. So that's 216 times 2 pi, 432 pi. So the cylinder has volume 432 pi. Alright, there's our final answer, and we showed our working because this was a written style question. 432 pi. Huh. Oh yeah, 430. For a second there I thought I said 232 pi, in which case the volume would be less than a sphere, and that definitely would have been a tell. But it makes sense, because the sphere should have a smaller volume. 432 pi, definitely bigger than 288 pi. So it looks like we're correct on B. Now we're on to C, another written style question. A solid cube with edges of length 1 kilometer is fixed in outer space. Darla, the baby space ant, that's weird. Darla, the baby space ant, travels on this cube and in the space around, but not inside this cube. Okay. If Darla is allowed to travel no farther than 1 kilometer from the nearest point on the cube, then determine the total volume of space that Darla can occupy. What is a baby space ant? Space ant, sure, but why baby space ant? This is weird. That's just weird. Okay. Well, putting aside the situation, which frankly is a bit nonsensical, we got a math problem to solve. So we have a solid cube in 3-dimensional space. So what does it look like? And our baby space ant can travel around it as long as it doesn't get any further than 1 kilometer away. But it can't travel inside it, but can travel along the surface area. All right. What to do? Well, this is similar to a question you can occasionally get. You'll have a... So this is similar to, I remember a question a number of years ago. There was a triangle, and a dog was tied to one end of it, and he had a fixed length of rope, and you asked, well, how far could he get? Like, what was the total area that the dog could get to? So it's sort of similar to that. It's like the baby space ant is tethered in some way to the cube, and that's sort of the idea. So it's one of those style questions. And for these questions, you had to break it up into, could they go along this part or could they go along this part? You got semicircular arcs, and I guess if we're in 3 space, we're not going to get semicircular and quarter circular arcs. We'll probably get parts of spheres and parts of cylinders, and that would explain why this is a C part to a question involving spheres and cylinders. So, sort of 3 different scenarios, I guess. So, Darla has sort of 3 options. She can be 1 kilometer from a point on a face. So she could be 1 kilometer above or 1 kilometer off on the side. And that's going to give her a very restricted form of movement. It's basically going to be a cube above, below, back, and front, and on the sides of this cube in terms of the space she can be. She can be 1 kilometer from a point on an edge, and lastly, she can be 1 kilometer from a vertex. So I'll show you what I mean. We redraw our cube. So in the first scenario, which we'll use the purple for, well, the mauve, I guess, lavender almost, she can sort of be up a whole cube's worth, because she can be at most 1 kilometer from any one of the points on this face here. Okay, how about green? Now, if she's from coming from an edge, she can sort of be anywhere on this quarter cylinder from the edge. Once we're at the edge, we have freedom of movement along here, whereas if we're in a point, you don't notice that you can sort of wiggle and curve around that point. You can just get closer to another point. And the last one, which we'll do with orange, I guess, she can be 1 kilometer from a vertex. So what is that going to look like? Well, we'll jut out, and we get sort of a weird an eighth sphere. This one's a cube, and the green one, which admittedly is a little harder to see now that we added our eighth sphere, is a quarter cylinder. All right. Now a cube has 6 faces, 12 edges, and 8 vertices. So we get 6 1-kilometer sided cubes up at the top, on each of the sides, that she can roam in. Okay? So this gives us a volume of 6. So there's 6 different faces, and then 1 kilometer cubed gives us the volume of the cube. So 6 kilometers cubed, and that gives us the purple case, which we'll again color code. All right. Now we have 12 edges. And that gives us 12 quarter cylinders of height 1 kilometer. Right? So imagine this guy's sort of on his side. A better one might be this one right here from this edge. But he's 1 kilometer high because that's the length of the edge. And he meets this cube and this cube, so he actually has radius of 1 kilometer. So that gives us 12 times, and then we have pi 1 kilometer squared times 1 kilometer. So r squared height. So that's 12 pi kilometers cubed. Right? Oh, but these are quarters. Let's do this on the next page. All right, we don't have 12 cylinders, we have 12 quarter cylinders. Twelve times quarter cylinder. Pi r squared h. That's going to be 12 times a quarter pi 1 kilometer squared times 1 kilometer. And that's going to be 3 pi kilometers cubed. Right? We've accounted for the 1/4. Now, in the next one, we're going to need to make sure we account for the fact that they are eighth spheres. So, cube has 8 vertices. And so, I don't know why I keep putting a comma there. I'm trying to put arrows. So, 8 eighth spheres of radius 1. We can go back and check our picture if we need to, but these guys are going to be an eighth of a sphere, and they're going to have a radius of 1 kilometer. So 8 times 1/8, 4/3 pi r cubed. 8 times 1/8. The 8th and the 1/8 will cancel out, but I'm just leaving it in here for conceptual reasons. 1 kilometer cubed. So that'll be 4/3 pi kilometers cubed. And those were each of the sectors that the baby space ant could move. How would an ant even fly in space? So what's the volume of the space that she can move? Well, 6 kilometers cubed plus 3 pi kilometers cubed plus 4/3 pi kilometers cubed. That seems kind of small, that last one. I guess the math checks out. That is the formula for a volume of a sphere. And so that's going to be, I guess we can group the pi's together. So that's 9 plus 4. So 6 plus 13/3 pi kilometers cubed. I'd write that out as a decimal because I don't like the way that that's left. I guess we could make it all over 3 if we wanted to. But you got to leave your answers as exact as possible. They didn't ask us to round or anything, so we're left with 6 plus 13/3 pi kilometers cubed. That's the area that our baby space ant can move in. All right, and I think that's all we were asked for. Determine the total volume of space that Darla can occupy. So there we go. And there's no D part. Just the back of the contest here. So that concludes question number 4. It's a nice little question. C certainly looks like it was probably stapled on there from another question, because we don't have a baby space ants in A or B, but C part definitely uses the formula for cylinder and sphere that we have already gotten accustomed to in A and B parts. So it's not a bad question. That baby space ant, that really confuses me, frankly. I want to know who made that question and why they thought a baby space ant would be good. But yeah, no. Good question. I'd say good paper overall. And that was the 2012 Friar Contest. So hopefully you liked it. If you did, throw a like on the video. Heck, just throw a like for Darla the Baby Space Ant. And as usual, you can get more contest videos on this channel, so stay tuned, and maybe I'll see you guys in another contest video soon. Thanks for watching.